Welcome to the 23rd lecture in mathematical finance. So today we want to first continue studying the mean variance analysis we started last time, and then we start talking about risk measures. But this is more an outlook for now. So let's come back to the mean variance analysis. So what we have is we consider a financial market which is allowed to consist of de-risky assets, and we assume that there's one trading period. So what you can think about this as well is how you can think about this as well is to say I want to follow a buy and hold strategy, so saying I buy now and then I keep for the next 10 years my position fixed and see how the market develops. And now I want to decide how I optimally decide what should be my position in the financial market. And then we introduced the following shortcuts, well, abbreviation. So we define MK as the returns of the kth asset. So the expected returns of the kth asset. And we also wanted to consider the covariance of the returns, which were sigma kj, which were the covariation of the returns of the case asset with the jth asset. For kj, and here we only care about the risky assets. So what we think about is if we want to invest in the stock market, and we have already decided which amount we want to invest in the stock market, and now the question is how do we select the position we want to have. And then we made the following assumption, which were first one was saying, okay, if I look at the vector of my expected returns and the vector E, which were the vector containing only ones, so they're linearly independent. And we want that the matrix containing all the covariances of the returns, okay, J, this is a D times D matrix, and this matrix is supposed to be positive definite. So morally, what we want to have here is a non-redundant market, saying that we really have assets which are truly new assets, and not that there's one asset which is just the linear combination of two others. Because then, I mean, this is not, I mean, it doesn't help us also to spread risk, because it's basically saying the third asset is just the combination of the two other assets. So we want to keep this in mind when investing and not treat the third asset as a single asset. All right, so this is the setting and the assumption we made. And now let's come to the problem we wanted to solve. And this was the mean variance criterion. So so what is the problem we want to have? So we decide, well, we have fixed level what our expected returns of our portfolio we would select should be. So we have given a strictly positive number MP, and now we want to solve the following problem. So this was labeled as P hat. So we want to find the portfolio, and here portfolio was just pi, so a real number, so a vector of d real numbers. So this is my portfolio. Right, so since we have here a one-step market, the trading strategies are just real numbers, real vectors. And now we want to minimize the variance among all these portfolios. And the variance was this, so we derived that this here is just the variance of pi. And we want to minimize the variance among all the portfolios which have an expected return equal to MP, right? This is what we derived also last time. This is the formula for the expected return. Of pi. And we also want that we have, well, that we cannot invest more money than we have. So we have the budget constraint telling us that this portfolio, if I take the scalar product with the vector E, so the vector which contains only ones as entries, has to be equal to 1. And this was the nominalization, how we defined portfolio. So this is our budget constraint. Right, which is basically saying we are not investing more or less money than we have. Okay, so this is the problem P hat we wanted to solve, or we want to solve if we in this mean variance analysis. So let us first see if we are able to solve this. So of course, we are able to solve this by what we have learned so far in the course. So what we note here is this P hat is a quadratic minimization problem. Minimization problem with linear constraints, right? So this is here quadratic in pi, and here you have two linear constraints, which you need to keep in mind when solving this optimization problem. Okay, well, that's nice because quadratic means it's convex, so we have a convex minimization problem with linear constraints, so we know what to do in order to solve this problem. So we want to consider the associated Lagrange function to this problem. And then we can write down our optimality condition, which leads to the Karush-Kuhn-Tucker point, and then we know by the theory we have developed that such a point is really a global minimizer of such a problem. So this is my Lagrange function here. So L, the Lagrange, depends on the portfolio, right? And now we need to keep in mind the constraints. So we need to introduce the Lagrange multiplier lambda 1, right, to model the first, or to keep in mind the first constraint. And now we have two constraints, so we need a lambda 2 as well. Right, so this is my function, my target function I want to maximize. So that's this. And now I need to normalize my constraints to be equal to 0. So I have lambda 1 or minus lambda 1. And this is the first constraint. So pi times m minus pm. Okay. And now I have a second constraint. So lambda 2 minus lambda 2 pi e minus 1. Okay. As I said, so our aim is now to find the Karush-Kuhn-Tucker point pi star with the associated Lagrange multiplier or multiplicator lambda star, which of course consists now of a vector in 2, so it's lambda star 1 and the lambda star 2. Okay. Right, in 2, and what are the defining conditions to have such a Karush-Tucker point? Okay, so what we need to do as before, well, we have done already a few times. So we want to take the derivative of the Lagrange function with respect to pi, so the variable we want to maximize over. Right. And let's calculate this directly. So what do I have if I take the derivative in pi? Well, this is why I wanted here to have the normalization 1/2, right? If I take the derivative, I lose the 1/2 here, and I get sigma times pi star, and now I have the other points here as well. So there's my lambda star 1 times m, right? Because here it's a linear function pi, and this is a linear function pi as well. So I have here lambda star 2 multiplied with p times e. Okay, that's, and now the other two conditions as usual, I mean, they're just our constraints of the optimization problem. So the first one was our constraint that the expected return of our portfolio should be equal to m pi. And then the second one was our budget constraint, so that p star times e is equal to 1. Now, to put here some grammar, we make some brackets, make some dots, and all right. Let's all right. So this is the problem. So we want to find this sorry. So this is the task we have. I mean, so we have here 3 equations and 3 unknown variables. So we need to solve this system of linear equations. And I hope you're all happy or familiar with how this can be done. So let me start doing it here. So how do we solve it? First, okay, let's check the first condition. Oh, the first condition is not. Of course, the derivative has to be equal to 0, right? This is the optimality condition. All right, so the first condition gives us what? The first condition tells us that pi star is equal to, right? This means I have to put the sigma on the other side. Lambda is a constant, so this is lambda star 1. And then I have to multiply it with the inverse of the matrix sigma, which exists because you have here a positive definite matrix. Right, and then times m, where this is this one, and then I have another one, so plus lambda star 2 multiplied with the inverse of sigma times e. Okay. And let me give this a number for later references. So this is equation 6.9. Okay. So if I take now 6.9 and multiply it with m, and I use condition 2i. So what do I get? So condition 2i is simple. So this here this condition. So my m pi is equal to okay, it's a scalar product, so I can swap this this order, so this commutes. So this is m times p star. And now if I multiply this equation above by m, well, what do I get? Well, yeah, I get m times p star. So this is the left-hand side of the equation 6.9. And now I get lambda star times m transposed sigma star inverse m plus lambda 2 star m t sigma inverse. Now I need this equation later as well, so let's give it a number, and this number is 6.10. And now again, I take my equation 6.9, multiply it with e, and use the last condition, which I haven't used so far. So 3 i's. All right. So what is this? So 3 i's tells me, well, 1 has to be equal to again commutativity of the scalar product e times m prime, and now so this is okay. And now I multiply the equation 6.9 with I. That's simple. M plus all right, and again, let's give it a number, which is 6.11 to use it later. Okay, that's nice. So if I look at these equations here, I have basically a system of two equations with two unknown random variables here. Good. That's correct. So if I look at this here, and I forget for a moment this equation here, right? I have a system of the two equations with two unknown random variables. I can solve it, and the moment I have solved this one, I can plug it in the last equation to get pi star. No. All right. So let's do it. Okay. So note these two last equations here are two linear equations with two unknown. Else lambda star and lambda 2 star. All right. So to make my notation shorter, let me introduce some short abbreviation here. So let us define the following constant. So this is A1. I mean, I take just here so I make so I define my coefficients. Oh, what's going on here? So I look at these two equations and I just label my coefficients to make my writing shorter. And the first one I label with A as this one. This is M transpose multiplied with sigma inverse multiplied with E. B is the next one here. This is M transpose sigma inverse and M. Oh, this is this one. C is what? E transposed sigma inverse. Yeah, E is the C, and now we also introduce D here, which is B times C multiplied with A, right? These are all real numbers, so these operations are simply defined. Remark that so A, B, C, D are real numbers, and we know even more. So because we have a positive definite matrix, the inverse is also positive definite, and this means B and C are strictly positive. Since what did I say? Yes, it's positive definite. Right. And we know even more since M and E are linear independent. We have that C times M minus A times E is unequal to 0, right? Because otherwise they would be independent. And this implies that my number D I defined here is also strictly positive. Why? So let's check this out. Since what we have here is, since the inverse of sigma is also positive definite, so we multiply it with this number, which is non-zero, right? This is what we have here, observed here. If we multiply this with sigma inverse, and then again, this number here, this has to be strictly positive because sigma inverse is positive definite, and now we multiply this out. Let's do this. What do we get? Right. No, a square E transposed sigma star inverse E. Right. Cool. How can I rearrange this? Well, let me look at the definitions. So the first one here is just a B. So what do I get here is C times B. Right? That's B. And then here I observe another A. So what do I get here is minus 2 times A square C, right? And minus, and this is another C, so this is A times C, right? This is C. So what else? So now I can pull out C to have C times the bracket in the BC, right? This is BC minus A square, right? Cool. Oh, because this is a plus, sorry, and this is and this is a plus as well, I guess. All right. Sorry. And this is now my B and my D, and this is strictly positive, so B has to be strictly positive as well. All right, that's good. So what do we have we learned here? So if we come back to our two equations, so 6.10 and 6.11, right? These are my two linear equation with the two unknown random variables, but now this can be rewritten as so B A C times lambda star 1, lambda star 2, and then this has to be equal to m pi and 1. Well, if I have such an equation, well, we immediately know what the solution is. Solution is, what is lambda 1 star? Well, this is C times m pi minus A divided by B, D. And the second one is, so lambda 2 star is equation. B times B minus MP divided by D. Okay. Okay, and now we apply using, so the first equation, we go up again. Right, so we solved now these two equations here. And so we can just plug in to see what pi prime, pi star is. So using equation 6.9, get P star is equal to CMP, right? This is just plugging in the definition of lambda star 1 and lambda star 2. Plus P minus AMP divided by D sigma inverse E. And pi star is a solution to our mean variance optimization problem P hat, well, because it's a Karush-Kuhn-Tucker point, and this means we can apply our results on convex optimization to obtain, and that this is actually, or to verify that this is a global solution, this is a global minimizer to the problem P hat. So this was contents of proposition 6.9. Yeah. All right. Okay. All right. So what else do we know? I mean, we can also now take this optimizer and calculate the minimal variance. Right. So this was the goal of our optimization problem, is to find this strategy which minimizes here the variance among all portfolios, matching our constraints. So let's calculate this as well. So note the variance of pi star is, so let's make this sigma. Wait. So let's make this to a definition. So this is why is there another? So of course, I mean, this is the minimum variance to optimization problem. So, oh, sorry. So this is, we plug in our minimizer times the covariance matrix times pi star, right? And now, well, we plug in what we learned. Okay, there it is, what we learned. That's nice. So what do we get? If we multiply this out, so this is B time divided by D minus 2 times MP A divided by D plus M pi squared C times D plus M squared sorry. And then, okay, let's pull this out. So that's M P C D plus 1C. All right. All right. Okay. So let's plug and so let's just summarize now the results we derived in the next proposition. Right. Okay, so this is proposition 6.19. So let me. Oh, okay. Let's stick to green. So what is our setting? So suppose we have a market which says, fulfills the assumption that the mean returns, so the expected returns, and this vector E, so they are linearly independent. And we also assume that sigma is positive definite, right? So this is the setting, and now we have given level of expected portfolio returns. This was given by m pi. Then the mean variance portfolio pi star. So the mean variance portfolio is just the solution to the mean variance optimization problem. So p hat is given, well, by the formula. So let me repeat the formula. If we have everything together here, plus right, and we also know that the minimal variance is given by the variance of this optimizer P star is, we just calculated it, so sigma square, depending on the given level of mean returns, is given by C divided by D times M minus A divided by C plus 1 over C. All right. So there's, we're in a nice position. There's nothing left to prove because this is what we have all derived now. So this is just summarizing our findings. It's always nice if we're already done with the proof before we state the result. Just one final comment is remark, or a couple of remarks. The first one is, well, the following observation. So if I look at so my mean variance portfolio M star, so I can rewrite this as linear function depending on the given level of the mean expected mean returns, and then I can rewrite it as a linear combination, actually here, convex combination, linear, because it might be not equal to 1. So linear combination of the following two portfolios. Right, and I need to tell you what G and HR. So we can just look at the formula here. If I want to split it up into this linear combination, so I rearrange it to all the terms which have no MP and the one which all have MP. And what I get is here G has to be 1 over D. A times 1 square M plus B D, and H has to be, well, all the terms where the MP appears. So this is 1 over D C times E. Right. So this observation, I mean, this is basically telling you if you, depending on the level, right? If you choose the level to be 0, then you only have here the G, and the other, if you choose the level 1, then you only have the second portfolio. So basically what it tells you is if you want to optimally invest in the market, in the sense that you use this mean variance criterion, you want to basically split up your portfolio into two portfolios, and then so these two portfolios are independent of the given level, right? So you basically split up, you choose two fixed portfolios, and then depending on the level of returns you want to generate, you put your weights more to the one or the other. And this is then called the separation theorem, right? So note here. Independent of MP, right? So the thing we observe here is saying, look, I can basically universally solve this problem, and then the optimal investment decision is just a linear function of these, I mean, combining these two given portfolios, right? So you define the portfolio G and M, and then depending on the level of returns, expected returns you want to generate, you move between these two portfolios. Okay. And the second one is, because this is, I mean, by far not the end of the story, is that you okay. And this is only the start of comprehensive. So, right, there's a really a highly developed theory, which, I mean, working with these mean variance analysis. Of course, you can also include the risk-free asset as well, and so on. So I here just wanted to present you the essential idea in our mathematical framework, and not. But you can, if you're interested, of course, look, for example, in the book of Nicole Boyle and Reader. They're also like, they also consider, for example, the case where you include the risk-free asset as well. But the techniques, I mean, you are able to solve it also by yourself based on the methods we have developed so far. So, comprehensive mean variance. Used by a Harry Markovich. Right. All right. All right. But due to time constraints in this course, I want to go on and not keep extending this nice setting. And going on means I want to come to our seventh section, which are risk measures. So what we discussed as the last thing was, okay, how do we invest in a market? And before we discussed how to sell and buy options or price options. And all these different type of trading, they lead to financial positions we have in the market. Right? So we have a financial position, which might be obligations, but also we have stocks and European, American option and so on, and they all might create gains or losses if we consider these combined financial positions. And one thing we want to do now is to somehow give a meaning, or to try to understand how it's reasonable to give a meaning to the risk we have when having this financial position in a market. And what this means is, this is what we will discuss today and next time. So, roughly speaking here, the aim is to measure, quantify. So in the end, we basically want to see our portfolio, financial position, options we have, and to assign them a value describing the risk. And risk is something, the downside risk, we understand. So the possibility that we face huge losses with some probability. The risk. So risk here is something negative in the sense of loss. Created by any type of financial position. As I said, this might be such a trading strategy, like a mean variance trading strategy, or so in the mean variance trading strategy, we try to minimize the risk in the sense that we want to have this trading strategy with a minimal variance. But here, we keep a general perspective saying, okay, we want to understand, how can we describe the notion, how can we reduce the notion of risk by in some sense. Right. Financial position, this basically, this is why there is some risk. So what is here? I mean, what to understand I've under the financial position. Represented. So financial positions are represented here, well, with our mathematical tools by a random variables. And so in the end, we have an underlying model given by some on some probability space omega, and then the payoff we see at the, say, terminal time is given by a random variable x. Right? And this might be a positive payoff, but it might be also a negative payoff if we invested or we're unlucky with our investments. So this is ED, linear combination of claims or terminal capital generated by trading. So, and I mean, we like to think about discounted quantities because, well, this is the natural way. So, this is right. So the terminal capital you get from generating, from trading in the market. So this can be any type of payoff you see at the end at terminal time t. So this is okay. And well, to make my life simpler, I mean, this is not a strictly necessary assumption here, let us consider only random variables which are in L1. We want that L is in L1, and what we you all know what the L1 space is, so these are all random variables. So X is a random variable such that the absolute value of X has a finite expectation. Okay, so you all know what this is, and I just assume that, I mean, if you have a finite market, this is always the case if you have a finite random variable. Right, so this is in our setting here, not super restrictive, but okay. I mean, it was also not necessary. This is what I want you to say. And now we want to assign such a financial position in the market, right? We want to assign this a number quantifying the risk we have. This X describes our terminal payoff at the maturity time t. I mean, for all our positions we have. So let me get definition. And this is the definition of a monetary risk measure. So this is definition 7.1. So what we do here is, I mean, we first abstractly think about what properties a risk measure should have, and then we consider more concrete examples. Right. So what is my monetary risk measure? So a map which maps, so it's a map row mapping from L1 to R. Is called monetary risk measure. If so, if we have the following two properties. So first is monotonicity. So monotonicity. This means so if for x, y in L, so if x is less or equal than y, this implies that the risk of x is higher than the risk of y. This is why would you expect it? So if you have always a higher payoff, and this is why risk is something negative, right? This is how the perspective we would like to take. This means if you have always y is providing always a better payoff, then the risk, the downside risk of y, so here in general the risk should be smaller, or at least not more. And the second one is, makes it to a monetary risk measures the translation invariance. So what it's telling me, if I have such a, so if I look at the risk of the position X, so financial position X, plus some constant M, so this is some money, right? So you add cash. This is why we like to talk here about discounted claims, because so this means just we put something in our bank account and that stays constant. Well, the risk of this position should be equal to the risk of X minus the money, right? Because if we add cash to our position, the risk should be reduced, and here we assume that the risk gets reduced exactly by the amount of money we added. So this is why it's a monetary risk measure, because it should be have these behavior in terms of money. Right. So, and of course, if we subtract money, so if we have a negative amount of money, then well, we move in the other direction. So let me put these remarks, the interpretations here in a remark, and this is remark 7.2. First thing is the monotonicity. So the downside risk of financial position get reduced if the payoff is bigger. Okay, this is okay. This is basically again a modeling assumption, right? You can disagree with the assumption I make here, but I want to convince them that they are, at least to a certain extent, rather natural. And then what's the second one? The translation invariance. So if we add cash and we add M of to our position, the risk get reduced by exactly m. Right? Well, this is, I mean, I think that the idea here is to say, okay, if I add really cash to some position, my risk should be reduced. And now I normalize my risk measure in a monetary way that the risk, I mean, the amount, how the risk is reduced is exactly m. Right? So, no, I think understandable way how to do it. All right. Okay. So what do we observe here? Just to so what do you see? I mean, if I have a translation invariant risk measure, so I look at, so I take a financial position X, so my random variable X in I1, and I add to it the amount rho. So the risk, the monetary risk assigned to this position X. So I add this exactly, right? Well, this is then a number in R. So the translation invariance tells me I can pull out. So this property, the translation invariance here, I pull it out, and you see, so the risk assigned to it is exactly the amount I need to add to my position to just assign it then a risk of 0. And if I look at the risk of something, of some cash position, so M is a real, I mean, this is number in the real, so this is just the amount of cash. Well, this is the same as 0 plus M, right? So this is this, then by the translation invariance, this is nothing else than the risk of 0 minus M. Okay. So for, okay. And I mean, if you normalize now your risk measure, and this is what happens in the second to be the risk of 0 is 0, well, then the cash has exactly, so monetary risk measure assigns the cash position exactly minus the cash position. Right. All right. Let us add to the definition of monetary risk measures some further natural properties we would like to have if we deal with the risk measure. This is the next definition, 7.3. So let us consider a rho to be a risk measure, a monetary risk measure. Right. So what properties we want to have? First thing is we might, I mean, the risk should not be depend on the actual realization of X, right? It should be only depend on the distribution, right? If you have two positions which in distribution give you the same payoff, you would probably assign to them the same risk. So this is called, so if we have this property, then it's called distribution invariant. What the, sorry. So if a rho of X is equal to rho of Y for X and Y have the same distribution. Okay. So the actual realization of the payoff is not important. It's what you care about is the distribution, how the, I mean, what payoffs you both get. Next thing is, okay, actually we want that risk measure appreciates diversification, sorry. So if we split our position into different objects, we want that the risk is not increasing, at least. So this is, I mean, in mathematical terms, I mean, the idea of risk aversion was leading to concave utility function, and now we swap here because we talk about losses, so we have a convex risk measure in this case. So convex risk measures. Well, convex risk measures, of course, exactly what you would expect by the name. Right, that's a convex function. So what is lambda? Lambda is between 0 and 1, and X and Y are in L1, right? Okay. Okay, let me finish the definition, and then I also give you, I mean, write down for you the financial interpretation, which I would try to, tell you verbally currently. And then the last thing is probably the most desirable one is if you have a risk measure which is coherent. This means there's a convex risk measure which is also positive homogeneous. Cool. Here, all right. So what it is, as I said, it's supposed to be. It is convex and positive homogeneous. So just to recall, I mean, this is as you know from real valued function, right? So from real analysis, some positive homogeneous means if you take a positive lambda and you pull it out, right? You can't pull out positive constant. So like for the Euclidean norm. Okay, so let me give you the interpretation, which I already said, but let me write it down because these are the justification why I want to have this definition. So that's the content of remark 7.4. First thing, so the assumption of convexity means that diversification does not increase the risk. So this is something which you somehow expect from a rather natural risk measure, that if you split you diversify your investment, the risk should not increase. It should basically decrease. And now, well, if you have a monetary risk measure, rho, which is supposed to be positive homogeneous, well, what do you have then? Then you exactly have this normalization property, which I mentioned, or discussed a few minutes ago, that the risk of the cash position 0 is 0. And how do you see this? So if you take rho of 0, then this is the same as lambda times the rho of lambda times 0. You multiply lambda with 0, it's still 0. Now lambda is supposed to be positive here, so you can pull it out. And this holds for all positive lambda. Right, and the only number which can fulfill this equation here is that 0. So you see, this has to be 0 and this has to be 0. Then this equation is always fulfilled, otherwise, well. Okay, that's nice. Now, yeah, and one last remark here. So if I take any coherent risk measure, I know that it is also sub-additive. Sub-additive. So what does sub-additive means? This means if I look at the risk of x plus y, this is less than the risk of x plus the risk of y. Right? Why is this the case? Again, this is a simple property of convex functions. So if you look at 1/2 the risk of x plus y, for the positive homogeneity of the coherent risk measure, I can pull in this 1/2. So I have 1/2 x plus 1/2 y. Now it's a convex risk measure, so I can separate these to 1/2 the risk of x plus 1/2 the risk of y. Well, and now I multiply everything with 2 to get the property I want to have. All right. Of course, I mean, this is somehow a rather strong assumption that the risk of the sum is always less than the risk of the single positions. right? Because if the position X and Y are correlated, I mean, strongly correlated, I mean, in the downside risk, I mean, that X and Y go bad might happen always at the same time. So this might be actually, the sum might be actually worse. So this is already, this is, to be fair, it's a rather strong assumption. All right. So let us now come to examples which are really used in banks or other financial institutions. And then we want to understand that these are this type of risk measures. So one of the traditionally most commonly used one, but of course there are a lot of criticism and better developed risk measures. But this is the way to start, is the so-called value at risk. So this is subsection 7.1, which brings us to the value at risk. In short, VAR. All right. So what is the value at risk is doing? It's based on the quantile function of a probability distribution. Okay, so let's consider the random variable on a probability space, right? This is anyway our setting. And we take a lambda between 1 and 0. So let me recall for you, and I guess you all have seen it several times in your life, the lambda quantile of X is the real number Q and R such that we have the following two conditions. The first one is the probability of X being less than Q is greater or equal than lambda. And the second one is telling me and the probability of Y of X being strictly less than Q is less or equal than lambda. All right. So if I have a continuous distribution, so if my distribution function describing the distribution of the random variable X is continuous, then this is one point, and here these two conditions are the same. But there might be, I mean, okay, there are many distribution functions which have jumps, so and then this might lead to an interval. Right, so there might be more than one number Q. So the set of all lambda quantiles of X is an interval, and that's the lower boundary is Q minus, depends on X and lambda, and the upper bound is Q plus, depending on X and lambda. And we know that these lower and upper bounds, I mean, they're the obvious definition. So this is the supremum over all X in X, such that the second condition here is fulfilled, so that the probability that x is less than here, okay, x is less than, strictly less than lambda, and this is what can be simply rewritten by saying the infimum of all x, so that the probability of x being less or equal than x is greater or equal than lambda. And the upper bound q plus, depending on x and lambda, is given by the obvious modification. So I replace here the infimum of all x in such that the probability of x being greater than x is strictly greater than lambda, and this is the same as the supremum of all x, x such that x being less than p is less or equal lambda. All right. Okay. That's the quantile, and okay, just to give you a curl definition, because some of you might have seen the definition of quantile in terms of the distribution function. So let me also recall this, in case you're more familiar with this. So in terms of the distribution function, fx, so this is the distribution function of the random variable x, which is just defined as the probability that x is less than small x. You can represent this lower bound q minus of x lambda as just the generalized inverse function of x, of the distribution function of x, which is just the infimum over all x in R, such that lambda of x is greater. So the distribution function, the first time the distribution function is greater than lambda, and the plus, so the upper bound, is given by the infimum over all x and x, such that the distribution function, the first time strictly bigger than lambda. And you see here, I mean, this is what I also said already, is the moment you have a continuous distribution function, well, the upper and the lower bound are the same, right? This is, you see, so the infimum that you're strictly bigger than x and the infimum that you're less or equal, greater or equal than lambda, coincide then, and they have 1 point. All right. Okay. So this is all we need to define the value at risk. Okay. Yeah. Definition. Oh, sorry. Definition 7.5. The value at risk and level lambda, lambda between 0 and 1, is defined by, so this is var lambda, so level lambda of the random variable x is minus the upper bound of the quantile x lambda. And well, this is the same. I mean, so this is the definition, and this is half lemma already. This is equal to saying, so you take the lower bound then of minus x 1 minus lambda, and this is the same as saying, or let's take the minimal amount cache m such that the probability of x plus m are strictly less than 0. So this is the amount of cache I need to add, and that the probability that I get negative is less than lambda. Next, so let me briefly show these last two inequalities. And this is, the rest comes next time. Right, so why is this true? So I show here that minus q plus of x given the level lambda, well, this is nothing else than minus the supremum over all x, such that probability of x being strictly less than x is less or equal than lambda. Well, then I pull in the minus, so this means the supremum swaps to an infimum. Right. And now we'll take this infimum. So let's do some relabeling here. So this is minus, and this is m. And the probability that x is less than m, minus m, sorry. So I'm just calling minus xm. So I have here minus, and this is the same as the infimum over all m, such that x plus m is strictly less than 0, has a probability which is less or equal than lambda. Right? So this is here the equality that the var is equal to this infimum. And this is the first thing. Second thing is, okay, I want to show the second equality here. So I start with the lower quantile here of minus x, given the level minus lambda, 1 minus lambda. So this is nothing else than probability, as the infimum of all m, that the probability of minus x less than m has to be greater or equal than 1 minus lambda, which is the same as the infimum of all m, such that minus x minus m, so I pull the m here on the other side, is greater than minus 1 is greater than minus lambda. Let me squeeze it here on this page. This is m, the infimum of 1 minus lambda, so I multiply with minus 1. And if I multiply an inequality with minus 1, this means I swap here the sign. So this is less than lambda. And this is the same as the infimum of m, such that x. So now I multiply this with minus lambda, so that x plus m is strictly less than 0. And here we are. This has to be less than lambda, right? So this is again here the identity. All right, So let me stop here for today. And next time we will start studying these definitions of the value at risk. We have defined it here and investigated as well, what kind of monetary risk measure it is. And of course, first of all, we need to show that this is monetary risk measure, and then we'll also discuss other properties and discuss a bit the value at risk, and then go over to other risk measures as well. All right, thank you very much for watching, and well, I hope you stay all motivated till the end.